In addition to semiconductors, metals also play an important role in solar cells. Metals make up the contacts that collect the charge carriers that are produced in the semiconductor layers of the solar cell. In this video, we will discuss some important physical properties of metals and semiconductors so that we can understand how the metals will interact with semiconductors in a full solar cell. Now let us first look at a standard crystalline silicon-based solar cell. On most common crystalline silicon-based solar cells, you will notice a metallic grid at the front of the solar cell. Depending on the solar cell design, metal is applied to the back and in many cases also to the front of the device, as can be seen in this cross-section of a standard crystalline silicon-based solar cell. The importance of metals is evident when we compare the conductivity of the semiconductor to that of the metal. In standard crystalline silicon solar cell, the N-type emitter needs to conduct the current laterally and has a resistance of about 100 ohms square, which for a micrometer thick emitter translates into a conductivity of 0.01 Siemens per centimeter. Although we can control the conductivity of silicon by the addition of impurities, the conductivity is still much smaller than of metals that are typically used in PV, like aluminium and silver, as is evident from this table. We see that the conductivity of metals is orders of magnitude larger than of the N-type emitter. Application of metals is therefore required to transport the photogeneration current with minimal electrical power loss. In this video, we will discuss some essential issues on the band structure of metals and how this is related to the electrical conductivity of metals. Also, we will discuss the work function of the metal, an important quantity which is crucial when discussing metal semiconductors junctions. Likewise, we will introduce the electron affinity, an important property of semiconductors. I will use the work function and the electron affinity later on when I discuss the metal semiconductor junction. Now first we look at the band diagram of a semiconductor. As you've seen before, in this band diagram we can see the conduction band in yellow and the valence band in blue, separated by a band gap Eg. For semiconductors, this band gap is in the order of 1 to 2 electron volts, and as shown before, this implies that at room temperature some of the valence electrons may be in the conduction band, given this material its electrical conductivity. This is illustrated in this slide by the blue section in the conduction band, representing the electron density in this band. If the band gap is increased, the free electron density decreases substantially, reducing the electrical conductivity. A large band gap makes it virtually impossible for electrons to be excited into the conduction band. Such a large band gap is commonly found for insulators. The absence of free electrons in the conduction band and free holes in the valence band of this material essentially implies that the electrical conductivity is extremely small. For metals, we have two possibilities. The first possibility is that the valence band is not completely filled, like is the case for copper or silver that only have one valence electron. As the valence band is not entirely filled, that leaves many energy levels in this band available for conduction. Alternatively, the conduction and valence bands may overlap. In this case, the valence electrons can also access the conduction band energy levels easily and are available for conduction. We will now focus on the band diagram of the metal only and level out the bands to where these are filled. As we have seen before, the energy level to where the bands are filled represents the Fermi level. In band diagrams of solar cells, the metal will just be represented by this Fermi level, indicated here with a red line. The vertical black line indicates the boundary of the metal, where the metal will make contact to another material. Obviously, the Fermi level is an important quantity in solid-state physics. However, when two different materials are in contact, we also need to take into account how well the electrons are bonded to this material. In order to get some understanding about this, we look at the photoelectric effect, first observed by Heinrich Hertz in 1887 and explained by Albert Einstein in 1905. This effect is based on the interaction of light with matter, in this case the metal. As you know, light has wave-like and particle-like properties. The particle-like properties are described by packets of energy called photons, and the energy carried by a photon is inversely proportional to the wavelength of the light. It was discovered that only short wavelength light, which carries a high energy, can release electrons from the metal. The explanation for this effect is that electrons in the material need a minimal amount of energy to be released from this material. This amount of energy is referred to as the work function and is defined as the energy difference between the vacuum level and the Fermi level. The physical interpretation of the vacuum level is that it is that energy at which the electron released from the metal has no interaction with the metal. The work function is often indicated by the Greek letter phi. Historically, this quantity often has been allocated to units of volts, and therefore in the band diagram the energy difference between the vacuum level and the Fermi level is indicated as the electronic charge times the work function. However, some authors prefer to allocate the energy unit electron volt. In this lecture, I will use the volt as the unit for the work function. The work function of some relevant metals for PV are shown in this slide, and you can see that values range from about 4 to 5 volts. Now we have a way to characterize a metal in the band diagram. We also need to look more closely at the semiconductor material. Therefore, we first draw the band diagram of a semiconductor, as an example in this slide an N-type semiconductor, and include the vacuum energy level. In this slide, we have lined up the band diagrams of the metal and semiconductor along the vacuum level. For semiconductors, the definition of the vacuum level is similar as for metals, namely that energy level at which an electron released from the material has no interaction with the semiconductor. Also for the semiconductor, we can define a work function as the energy difference between the vacuum level and the Fermi level. For semiconductors, the definition of the vacuum level is similar as for metals, namely that the energy level at which an electron released from the material has no interaction with the metal. Also for the semiconductor, we can define a work function as the energy difference between the vacuum level and the Fermi level. The Fermi level expresses the electrochemical potential of the electrons in the material and can be loosely interpreted as the average energy of the valence electrons. In addition to the work function, we have another important parameter, the electron affinity. This is defined as the energy difference between the vacuum level and the bottom of the conduction band. The importance of the electron affinity is that it is a specific fixed material property, whereas the work function of a semiconductor can vary by changing the doping concentration in the material. This slide shows the values of the electron affinity for some typical semiconductor materials, and it is evident that the values are around 4 volts. Before we finish this video, I would like to spend a few minutes on how the energy differences should be scaled in a band diagram. And I do this by taking into account the band gap of the semiconductor. The band gap is the energy difference between the bottom of the conduction band and the top of the valence band. And for the sake of clarity, I will draw this difference smaller and take silicon as an example. The band gap of silicon is 1.12 electron volts, and when we look in the table, we see that the electron affinity of silicon is just over 4 electron volts. If we were to draw the electron affinity to the correct scale in the band diagram, this energy difference should be 3.58 times the band gap energy. Drawing this band diagram, we see that in this specific case, the vacuum level should be drawn lower, like is shown here. Usually, when drawing a band diagram, we are more interested in the conduction and valence bands rather than the energy difference with the vacuum level, and therefore we put more emphasis on those energy levels. In order to include the vacuum level in the drawing, we tend to draw this level closer to the conduction band, which is not quite correct. However, we indicate this in the band diagram by drawing a cut indicating that this energy difference in reality should be larger. In summary, we have explained the large conductivity of metals by the Fermi level being in either the valence or conduction band rather than in between the two bands, as is the case for semiconductors. I have introduced the concept of the work function, which is defined as the energy difference between the vacuum level and the Fermi level. Likewise, I've introduced the electron affinity, which is defined as the energy difference between the vacuum level and the bottom of the conduction band.